Work with me on this. This is the matching problem, right? So this is problem 1 of the test. Basically, you have a transmission line and you have ZL here. And ZL equals something. Is it 25 plus J40?
J45.
25 plus J45. I'm going to just go ahead and normalize it. Divided by Z naught, and Z naught is 50, I believe. Is that right?
Yep.
And that comes out to 1/2 plus J, and that's 0.9, correct? All right, now that's an impedance. Remember, it's a series type matching, so we're working in the impedance domain. Y'all with me on this, guys? All right, so I'm going to try to sketch this. I have the Smith chart that I'll provide for you. I'll put the solutions up when I'm done. And it looks something like this, right? That's the one circle. So if you're looking at 0.5, it's a circle about here, just trying to crude estimate. And 0.9 is back here. So this is 0.1, and that's ZL. That's the first point I should have seen. Y'all follow me, class? Sometimes, some people didn't label their things and they had dots all over, but you have to indicate to me what you're thinking and why you're doing it. So that's the first point, ZL. Next thing, you're going to take, there's no order to this, but come out here and you're going to see something that's going to give you the mile marker, wavelengths towards generator. We'll get that in a second, but I want to make sure you all see it, right? Next, we're going to go ahead and get a circle of radius right here, from here to here. And you're just going to describe that here. And it's going to hit 2 points on the one circle, here and here. Y'all with me on this, class? Now, this is an inductor that we're going to use. So somewhere down the line, we're going to put an inductor, right? An inductor has plus J value. I'll put the impedance down. It's plus J times omega. And normalized divided by Z naught would be the value. It's a positive J is the point I'm making. Right, class? Think them over. If you miss this, you're going to see this again, this kind of stuff. You better be really... I want you to make sure you learn how to use the Smith chart and why we're doing what we're doing. People oftentimes have large gaps in the reasoning. They just know that's how we did one problem. They don't understand the entirety of it. So I'm trying to make sure you do, because you're going to get another problem on the final for sure, okay? And you're going to use this again in EMAG 2, and you'll probably use it in other courses. So that's point 1. Now, since that's a plus J impedance when it's normalized, we have to hit a point where there's a minus J on the input. Y'all follow me? Mm-hmm. That's this point. This is going to have a value of 1 minus J something, and I'll get to that something in a second. And then you draw a line straight from the center through here, and you're going to get a mile marker wavelengths towards generator here. There'll be a mile marker wavelengths towards generator here. Now, I could look it up, but a lot of people got this one. What's the mile marker here? I want the outer one. Wavelengths towards generator.
128.
0.128?
Yeah.
0.128 lambda. Anybody confirm that? It's about that.
That's what I got.
I'll post I've got the actual values. And down here, what is it?
I got 0.325.
0.325. Y'all agree with that?
Yep.
If you didn't get this right, look and make sure you see these values. I'll take a moment. I want to make sure everybody sees this, because this is not a hard problem. This is actually the homework problem. I don't know if you recognize it. It's the one that we did. We did with an inductor and a capacitor. I believe I did this whole thing on the board. I'll have to check the video and make sure, but I think I did. Anyway, so for this one, this length right here to where the inductor connects, right here, in wavelengths, L would be equal to the mile marker where we ended up, 0.365 minus the mile marker where we came from, 0.128 lambda, and just briefly, can you
0.197.
0.097?
197.
0.19, that sounds right. 0.197 about lambda. So that's, okay. Now, y'all follow the reasoning. Remember, it's series. We're not in the admittance domain. Several people in the admittance domain, I did not understand that because I said series inductor, but a lot of times people are reactive. They're not thinking. They're just knee-jerk. Okay, now here it's 1 minus J something. I think it's 1.45, but I'm not sure. Tell me.
Yeah, I got
I got about that.
It's about minus J 1.45 something, about there. It's normalized, correct, class? Now, that has to be equal in magnitude to the inductive impedance or reactance. Everybody with me? So here I say 1.45, and this is normalized. This is going to be equal to omega L, it could be J omega L, but just omega L, and it's got to be divided by Z naught. Now I'm putting that up here for a reason. Some people use the capacitor for some reason. When L is inductor, when I say inductor, it means inductive reactance, positive J. Y'all with me? Now, after that, to get L, it's going to be 1.45, approximately 1.45. And then it's going to be times the Z naught divided by omega. Omega is 2 pi F. And was F 1 gigahertz on this one?
300 megahertz.
Oh, even better, 300 megahertz. Okay. So that comes out to 1.45 times 50 over 2 pi times 300 and times 10 to the 6. And this will be in Farad, or in Henrys, but it'll be nanohenries, I think. What did you guys get?
I got about 40 nanometers.
How much?
About 40.
I think it's 39 point
I
something.
got 38.5.
I got 39.8. Yeah.
It's close to that, somewhere between about, I'm gonna go about 40 nanohenries. It's rough. I got the exact value, but I give you credit if you got close, all right? I'm not worried about it. You all with me? All right, so that's what inductance would go there. That's part one. Any questions before I move on? This is one that's very important to know, because you'll be asked about parallel in series, both shunts and elements, where you use either inductors or capacitors. All right, so I want to make everybody, I want to make absolutely sure that there's nothing you don't see here. Y'all with me? All right, what about the next part? It says now I'm going to replace that inductive reactance with a shorted, I believe, right? A shorted stub in series, correct?
Mm-hmm.
I'll draw it over here. I want to make sure everybody sees this. Some of you remember this problem. I did this in parallel and series for the impedance matching or shunt matching, and I did this with capacitors and inductors. Almost the same exact problem. The load was a little different, but it was similar. Okay, now what we're going to do is this. We're going to attach it at the same point that the inductor was attached. Here's my ZL. This distance is going to remain the same, 0.197 lambda. And now I need this length. It's L of stub, right? Correct? And that L of stub normalized has to be equal to J 1.45. It has to be this. Y'all agree with that? Plus J 1.45. Y'all with me, class? Now, it's a shorted stub, so on a Smith chart, I'm going to use a Smith chart. I want everybody, please be attentive here. Make sure you don't make this mistake again. Y'all with me on this? Follow me. So it's shorted, right? If it's shorted, what's the impedance? Impedance. Zero. Normalize it, 0, right? It's an impedance. Where do we start? Right here. This is 0. Not here. Y'all with me? We're not in the admittance domain. It's impedance, correct? Now, how far do I have to go?
All the way to J.
Until I hit what?
J 1.45.
Right here. This should be J 1.45, right? And if you take a line and go right through there, you're going to get something that is wavelengths towards generator. Can you give that to me?
I got about 0.156.
It's about there. Anybody? What did you guys get?
154.
And again, I'm going to say one thing. Your Smith charts, if you don't proportionally enlarge them, sometimes it's just the ink, then you're going to get a slight difference, but I give you credit if you had that. So what is this, 0.1?
156.
156-ish
Right,
lambda. Now that means, because it has to be plus J, y'all with me? It's an inductive reactance that's exactly the same as the inductive reactance for the inductor when it was there. So that means this length here that I drew is this. It's going to be 0.156 lambda. Are you all with me? got a question for you. I want you to think about this. This is the kind of stuff I might ask. Hint, this is the kind of stuff I might ask. I hope I'm getting through. All right. Now, what if I say I'm going to make an open circuit? We're going to start there. What if it's an open circuit? What changes?
We start at,
You start on the right.
on the right side of infinity.
And we go all the way to that point. We go a full, what, quarter wavelength further, right? All right, so we'd add a quarter wavelength to the prior one. Do y'all follow me? Now, I'm not done yet. Y'all with me on this? Hear me now. Now, what? This is one of these things, oh, God forbid you do it, Dr. What if I put a capacitor there, and I want to just listen before you react. A capacitor with a reactance of, say, minus J50 ohms. No, maybe minus J, yeah, 50. That's what I want. So, I want you to figure out the length such that this will match it. Now remember, a capacitor doesn't absorb energy. You can do matching with a capacitor. Go ahead.
Oh, no. Okay.
Or you normalize it first, right?
Yeah.
Minus J50 by 50 is minus J1. Do you all agree with that? Where's minus J1?
The very bottom.
That's minus J1. All right? That's where you start. Remember, there's no real part at all. It's right on the edge. You all with me? Well, how far do you have to go? If that's the impedance, you want to go to here and make it, say,
Just go all the way around back to the top.
now you're going to what? This point where it's plus J1.45. Do y'all follow me on that? Everybody? That would be the length. Got it? Now just think of the reasoning, right? I'm not done. Y'all with me?
Yeah.
What if it's an inductor? You wouldn't do that. I would. Make it plus J50.
Now you start from the very top.
Start from the top.
Yeah, this is the crazy one, right? Now I start just shy of that point. Well, actually, here's the point, right?
Yeah.
All right, I barely move and I'm there, right?
Yeah.
So really, if I forced you to maintain the fact that it has to be at least of a tenth of wavelength, then I have to go one full wavelength plus that little bit. Y'all, or one half wavelength plus that little. Y'all follow me on this? See the reasoning behind it? Now this is a series. If it was shunt, you'd do the same thing. Just reason your way through it. Y'all with me, class? Now that hint is for the final exam, and I hope to God you guys put down. Dr. Baginski talked about replacing the short with an open or an element, either an inductor or capacitor in parallel or series. Got that? Just to make sure everybody knows how to do this. Okay. I can't be more clear. I mean, I could be, I suppose.
It's recorded. If you
What?
don't watch the video, it's recorded. If you don't watch the videos.
Hey, I've learned my lesson with that. I don't assume anybody watches the video. When I get questioned, but you never talk. Have you? What? That's the best one for you. Never mind.
Yeah, I can see us watched it. It's not very big. But
I
You
really
see the
appreciate
reviews.
you recording. I mean it. I mean, some people do. I bet you the people that aren't here, honestly, several of them, I know will watch it. And I can't say this with a whole lot of confidence, but whenever I get questions from people that I don't recall being here, I figure the only thing I could have done is done a bit, or they did the homework and they were a little puzzled by something. But I'm glad we're recording. I wish all these lectures in Auburn were recorded because frankly, there's no downside. There really isn't. The students miss a class, you can go look.
wow, this is so stupid.
Okay, let's do problem. Any questions about that before I move on?
Nope.
I thought that was very fair. I literally took a homework problem and I did the one I worked on the board. That's the reason I did that. Next one.
It's the. You know, just read it.
Just
It's
read
the-
it.
A charge 6 microcoulombs
This is on the z-axis.
is located at 0010.
All right, so it's 10 meters up, right? This
Yeah.
is the distance up it is. I'm just going to call it Q, and Q is equal to 6 microcoulombs, right?
Yeah.
Then there's an infinite line charge on the x-axis, right?
Yeah, on the x-axis.
All right, so I can draw this kind of sort of. So here we have an infinite line charge, rho L, on the x-axis. Now, you did a problem just like this on a quiz, only it didn't have an infinite line charge. Do y'all remember that? The only thing you had to do is figure out where the E field 0 on the z-axis between the two. It's just like the quiz problem, except I use an infinite line charge, not a point charge. Y'all with me? So somewhere between here and here, this is an infinite line charge that has rho L. The electric field is going to be 0. Now here's how I'm going to do it. This is a line charge. If I take a look at the electric field at any point here from the line charge, it's pointing up. I'll call it E, and I'll call it L right here. So EL, in terms of the coordinates I gave you, and this would be in the positive z direction, would be rho L over 2 pi epsilon naught z, and it would be in the positive AZ direction. It's not necessary to add all this detail, but I'm doing it. Y'all with me? Now, and you have to know the electric field from a line charge, from a surface charge, for a surface charge density from a point charge. These are must-knows, like F equal ma kind of thing in physics. You gotta know this. Next, what's the electric field from a point charge cube? Well, the electric field from a point charge at any given distance, first the distance difference here would be what? It'd be 10 minus z would be the difference in these 2 points. Do you agree? Remember, it's between the two. Correct, class? Here, it would be pointing down, right? So I can call it EQ here, and it's pointing down. EQ technically would be equal to minus the charge Q over 4 pi epsilon naught. Then it would be 10 minus z squared, right? In the AZ direction. Does everybody follow my logic on?
Wouldn't it be? Oh wait, yeah, no, yeah.
You just did it.
Yeah.
Yeah, that's fine.
I mean, are you all with me on this? Now, if you add the two together, you're going to get, we're looking at the point where there's 0, correct? So we'd say that EL plus EQ equals 0. That means one is equal to the negative of the other. I'm going to go there. Y'all agree with that? Just take a moment, make sure what I'm saying is sinking in. Y'all with me? Okay. So now I'm going to take this one and I'll say it's rho L, whatever rho L is, over 2 pi epsilon naught z. We're going to figure out what z is in a second. Over, and it's going to be q. Remember, the minus sign, when it's flipped to the other side, goes away. Over 4 pi epsilon naught. And then it's going to be times 10 minus z squared. And here again, I'm not doing anything fancy. I'm just going through the motions of equating. Everybody with me? One of the first things you'll notice is the epsilon naughts cancel and the pi's cancel, if you're honest with yourself, right? So I'm just going to get rid of the pi's and the epsilon. Right? Now after that, and this is totally up to you how you do it, I can go ahead and I can flip both of these, right, because it's an equal sign, so I can say that I have, in this case, I have 2z over rho L, doesn't matter how you do it, is equal to 4, and it's times 10 minus z quantity squared over q. And it's totally up to you how you do it. Do you all agree with this? You're solving a quadratic at this point. You're going to get 2 roots. One of them is allowed between 10 and 0. The other one is disallowed because it's not between, it's negative. You all with me? Okay, now at this point, I'm going to go ahead and just divide both sides by 2 just because I'm trying to make it a little easier. And then I'm going to multiply both sides by q. You don't have to do it this way. Actually, what I'll do is divide by 2 again. All right, so, sorry. Wait a second. Hold on. That should be 4, right? And that was 2. Okay, now, here's what I'm actually going to do. I have q over here. Right? Q is down here, now it goes away. And now I'll just do this right now. Let's see. I'll divide both sides by 4, so it'll make my life easier. It means it's divided by 2. I take a look at this. I have q. I have, on one side, I have z over, and there's a 2. Rho L is, what was it, 180, something like that?
It was, yes.
180 times 10 to the minus 9 over 6 times 10 to the minus 6, right? and then it's times z equal to, or it's got times z, is equal to, in this case, just 10 minus z quantity squared. So now, really, I'm going to get a single number here. Z, let's see, what do we got? 10 to the 6, 10 to the minus 9 means, let's see, really good. 10 to the minus 9, let's say minus 7 to minus 6. We can get rid of that. So we have 6 over 2 times 0.18, right, is equal to 10 minus z quantity squared. I square these things out, and I'm going to get z squared, right, minus, and it's going to be 20z, and that's going to be plus 100 is equal to this. What is this number here, by the way?
It's about 50/3. It is 50/3.
All right,
Yeah.
so it's z times 50 over 3. Take that to the other side, so now I have 0 is equal to z squared, and it's minus the quantity 20 plus 50 over 3, z plus 100, and that's all equal to 0. So this is a root solver. A will be equal to 1, B will be minus 20 plus 50 over 3, and C is going to be 100. And the roots are going to be, there'll be roots 1 and 2 for Z equal to minus B plus or minus the square root of B squared minus 4AC all over 2A, and A is 1. But that's the root solver. Y'all with me in class? Now, you don't need you can have a slide rule that you do this. That right there is a constant, B squared minus 4AC. B is right there, when it's a minus sign, it's plus that, so you have plus that number B, a magnitude of B, plus or minus that over 2, really. And you're going to get two roots. One is about, I think it's about 2.97, but I don't remember exactly. The other one is negative Z. The only root you care about is a positive. What did you get for Z? For the root positive?
I got 2 point. Well, they were both positive for me.
Okay, go ahead.
2.97.
Can't be both positive. That's, I don't believe it.
No, I got the minus. Well, I saw the.
One of them's negative.
They are both positive.
No, they're both positive.
The minus one is still positive. The minus one's the one we use.
Yeah, 2.97 is the minus one. It's just the B was bigger than that over there.
Whoa.
Okay, all right. You got two positive roots for that?
You get 33.
Yeah, I got 33.7 and 2.97.
Yeah, but it's outside the range.
Yeah.
See,
Yes,
Z
yes,
between
yes.
0 and 10.
Yeah, we're
Yes,
outside
yes,
the
yes,
range.
yes.
I should say it's outside the range. This is the one that's inside the range.
Yes.
My bad. All right, so this is the actual place you would locate it. Now, it's
Yeah.
just a simple quadratic, and you have to be able to solve these things if you're an engineer. You do. Really. All right, I mean, some people, you can make goofy mistakes, but in tests, you have to force yourself to do the boring, mundane stuff correctly. That's the real difference, in my opinion, between some theoretical physicists and some high-paid engineers. They both know the same thing when it comes to electromagnetics and radar and all that other stuff. Problem is, engineers are paid a lot of money to be careful and exact, and they usually double check their stuff. You probably heard about things like space shuttles blowing up, and the time they messed up with the Mars rover. Those were unit mess-ups, believe it or not, for the Mars rover. The other one was they didn't even test the O-rings. That was for the space shuttle. And when it was at even liquid nitrogen temperatures, there was liquid oxygen. Make a long story short, engineers can't afford to make mistakes. They're colossal amounts of money you can lose, so you have to double check. Y'all with me on this? What's the second part?
Find the electric field at Z equals -10.
Okay, so now we're down here. Now Z is minus 10, right? I don't think I took anything off if you didn't put a minus sign. Right, it's going to be in the negative direction. Do y'all agree with this?
Mm-hmm.
All right. So to get that E field, you got two sources. One is this infinite line charge. Is going to give me an E field here. It's just rho L over 2 pi epsilon naught divided by 10, right? And it would be in the minus AZ direction. Do y'all agree with that?
Yeah.
Then you got to add the one from this. Well, this is actually 20 meters, right? Because this is 10, this is minus 10, so it's 20 meters. So it's going to be this Q divided by 4 pi epsilon naught divided by 20 squared, and it's negative as well, right? So the total electric field, this is for part B, I guess, is going to be equal to, and I'll just put this down, it's q over 4 pi epsilon naught, and it's 20 squared. These will be minus, I'll put the minus sign out here, then it's going to be plus rho L over 2 pi epsilon naught, and it's over just 10, right? And both of these are negative, so that will be the value. Can you give me that value, by the way?
What the final answer is?
Yeah,
458.6.
that's right. 458.6 volts per meter AZ. Now, if you didn't put volts per meter or AZ, you were forgiven, but you have to get that value, and it had to be shown to me. Y'all with me? Okay. That's that problem in a nutshell, I believe. I don't think this is enough. Next problem. I thought it was supposed to be representing the quiz that we did. All right, fine. Next problem.
Let me just read it out. A spherically symmetric charge density is given by rho v equals 1 over r nanocoulombs per meter cubed.
1 over r as nanocoulombs per meter cubed. So that's
And
a charge.
that's for r less than a.
All right, so this is true for r less than a. Let's go ahead and put an a thing out here. All right.
And then it's 0 for r greater than
So
a.
all the charge is limited to that spherical, the inside of the spherical shell. That's the density, right? Now this is, let me remember me doing this exact same problem on the board. Anybody? It's the exact same homework problem with one exception. This had a slightly different form.
I was like
but it
1
was-
over
Yeah,
squared,
yeah.
yeah.
It is the same exact technique. Everything was different except the charge density was slightly different. So here, you know that the integral, we're going to go for r less than a. So we know the integral of d dot ds, I was very glad to see a lot of people get this part right, is equal to the integral, well, if you're inside there, it's the integral of rho v dv inside the volume that you specified. You all agree with this? So my volume, since I'm inside, is going to be limited to r. And now I'm going to try to find the d field, and it's radially outward. We know that the d field is going to be symmetric with respect to phi and theta, radially outward, and the magnitude of the d field is not a function, I mean, it is constant at a given r, no matter where you are. So this, now you remember me saying this is really a surface area of a sphere times the d field. You all remember? I can put down the formal integral, there's no need to it. This is 4 pi r squared d of r is a function of r. And any form like that, you got credit for. And that's equal to this. Now that's a volumetric integral. A lot of people recognize this. So I have technically a triple integral, right? And I have I have to put the charge density, so that's going to be 10 to the minus 9th over r, because it is nanocoulombs. Then it's times the differential volume, and I gave you that, if you look. So then I'm going to take it times r squared, and it doesn't matter the order. I'll go d theta, d phi, dr. And technically this should be primed. And here, r will go from 0 to r. Theta, or phi, I'm sorry, from 0 to 2 pi. And theta goes from 0 to pi. And there's a sine theta, I've forgotten here. There's a sine theta that should be there, I'm sorry. Y'all agree with that? You all with me?
Yep.
All right, now I'm going to go ahead and do this once. Usually I don't bother, but over here, first thing I'm going to do is take the 10 to the minus 9th out in front. Okay. Now, the next thing is I see the r prime and r squared. One of them is going to cancel. It's just r. Do you all agree with that? So that means I can get rid of that r squared over r and just make this r, or r prime. So I take the 10 to the minus 10th out in front here too. Or 9th, pardon me, 9th. So 1 times this. And there's a sine theta. So when I integrate d theta sine theta, I get minus cosine theta evaluated from 0 to pi, is going to be minus a minus 1 plus, it's going to come down to what? 1 minus a minus 1 or 2. Do y'all agree with that? Then when I integrate phi from 0 to 2 pi, I get 2 pi, so it boils down to 4 pi comes out in front. For this integration will always be the same for over a spherical region. Now I have to integrate r, dr. That's going to be r prime squared over 2 from 0 to r, or it's really going to be r squared over 2. And remember, that's equal to 4 pi r squared dr of r. Do y'all agree? Now here I'm just, I want to make sure you're with me on that. I'll slow down. But this is supposed to be, this is meant to be just really a template kind of problem. You go through the method in your brain, just put it on paper. There's no tricks on this one. It's an easy answer to it. If you look at this, one of the things you notice, the 4 pi goes away. Next thing you notice, the r squared goes away. It's constant. It's just 10 to the minus 9th over 2, the d field. Anywhere between 0 and a because of that charge density. So the d field equal to, in the radial direction, I'll call it just d of r, is simply going to be 10 to the minus 9 over 2, and that would be coulombs per meter squared in the AR direction for r greater than or equal to 0, less than or equal to a. That's all it is. It was a straightforward answer, almost trivial to get it. You all with me? Next part. Here we go for r greater than a. Well, again, put the integral up. Integral of d dot ds. This is what I'd like to see so I know what you're thinking. Is equal to the integral. And here it's a triple integral of rho v. I'm going to leave it as just rho v here in a second. And times r squared sine theta d theta d phi d r. And I'm doing that for a reason. Remember, the rho v is just this. It's 1 over r times 10 to the minus 9. Can you all follow me on this? You good with that?
Oh, yeah.
If you need more time, let me know.
No, I'm just ready.
All right. Now, this is still going to be from 0 to pi. This is still going to be 0 to 2 pi. It has to be. The r changes the limits now. It can only go to a, because outside of a, it's 0. Do y'all follow me in that class? So it goes from 0 to a. Now, I can put the charge density in there, the rho v. Do y'all agree with that? So I can put it in as 10 to the minus 9 over r, or just divide this by r and put the 10 to the minus 9 down in front. And now you can see the r squared over r, it becomes a single value of r as before. And we can go ahead. That integral becomes 4 pi r squared times d of r on this side. Now we're going to get 4 pi right. When we integrate, that's 4 pi is when we do the sine integration, the phi integration. So sine theta d theta d phi, just surrender 4 pi. When I go r dr, I got r squared over 2 from 0 to a. That means this becomes a squared over 2. And I'm just putting it down exactly. And it's times 10 to the minus 9th also. 10 to the minus 9th. Do you all agree with that? Now, at that point, the only thing you're doing is canceling the 4 pi's. And now you're going to see that d of r is going to be, doesn't matter how you do this, you can put a over r squared and 10 to the minus 9th over 2. And that would be in the AR direction, coulombs per meter squared. And that's it for r greater than a. And that really was what I wanted to see. Now, on final exam, I'm likely to give you a cylinder, all right, instead of a sphere. Follow me on this? So now the geometry changes. But I could give you a sphere. I could give you a planar thing. The idea is make sure you know the methodology, the way to do it. Y'all good with that, guys? Any questions before I move on? I thought that was a very straightforward problem because I gave you basically that. I even did this one on the board basically without rho v being that form. I think rho v was a function of r, but it wasn't that function. You can check back. There are several problems I gave you like that. Any questions? Okay, next problem. Hold on. Let me erase it. somebody, besides Chase, I think somebody else missed this exam.
Andrew Strickland?
Yeah, I think, why?
No, that's who it was. I
I
don't
mean,
know.
but you know him?
No.
This is a guy.
Because
You just said his name last time.
The guy that sits right here, I think. I don't know.
His name's Simpson, Chase Simpson. I messed him up. This is Andy. You haven't seen him?
Did he email me? I don't know. I don't know. I didn't really know him.
If you see him, give him a heads up that can't help people. They don't, interact with me. And I hate to see people. I've had this happen. People just forget about the class and fail. It's like, I didn't know I was taking it. I had a kid one time miss the final exam, showed up the next hour. I don't know what to do. I mean, it's over. Okay, next problem.
Determine the capacitance for a spherical capacitor.
So this is cap resistance, right?
Yep.
Okay,
Yep.
so I'm going to set it up, and this is another problem that we talked about. The big deal here is the dielectric changes. So for the capacitance, we're going to ask for resistance too in a second. As an inner radius A, outer radius B, right? And it's filled with something that has a dielectric of we use this. The dielectric constant is, I forgot what it is. What, can you give that to me?
It's 3 over R.
3 over R, and that's a relative dielectric constant. You have to multiply that by epsilon naught. Y'all follow me?
Yeah.
We get this. So this is the thing, and think of this as having a capacitance like so between these two plates. You got an outer conductor and inner conductor. Technically, if you're going to make a spherical capacitor the way they do, they're going to drill in here, put a little thin bit of insulation, and then a filament goes and connects to this metallized surface. The outer surface is metallized and grounded. And the reason they do this is, and you'll see this in a bit, the inductive reactance is 0 between the inner and outer one. There is no inductive reactance. It discharges super, super fast. That's what I'm going to tell you. And I'll show you this later. But anyway, for this particular one, it's a capacitor. That's epsilon relative. So the steps you do, first step is you assume something. We assume a charge. We'll assume the charge is totally right here on the inside. You could assume rho s if you want, but it's a charge. Y'all follow me? It's uniformly distributed around the inside. Now after that, come out here at distance r, and I put my little Gaussian surface, right? And I say, well, I know the integral of d dot ds over that surface has to be the charge enclosed. Do you all agree with that?
Mm-hmm.
Take a moment if you don't see it. The integral of d dot ds, this is my Gaussian surface, it's between A and B, it's a spherical surface, it's concentric with that, the center of this capacitance. You all with me? Now, when I go ahead and integrate that, so I got Q, now I get D, so the integral of d dot ds over the closed surface is charge enclosed, which is Q. This is 4 pi r squared times d of r is q, therefore d of r is q over this. So from here I get d of r is equal to q, my assumed q, over 4 pi r squared in the AR direction. I'm going to omit the units, but you all follow me. But that's the D field. The next thing I get is the E field, right? And I'll slow down for you too. So to get the E field, I just take the D field divided by epsilon. You guys got me on this one? Epsilon is epsilon naught times epsilon relative. So here, it's equal to the assumed Q over 4 pi epsilon naught epsilon relative. I'll leave it as epsilon relative for now. Over r squared AR. And now I'll put in the value for epsilon relative. Remember, that's the formula, right? That's the general form of this thing, is d over epsilon. D doesn't matter about epsilon, but this does, the E field. So here, it's going to be Q over 4 pi epsilon naught, and then epsilon relative is 3 over r. So I'll write it down this time. 3 over R divided by R squared in the AR direction. And if you wanted to put the units, it would be volts per meter. I want to make sure everybody sees this before I continue. You understand? I'm just sticking in the value for epsilon relative directly, right? The thing that's obvious is this R and this R cancel. Can you all see that? So I just get an R. Becomes 3 over R. And I can rewrite that. I can say therefore E, if I wanted to get a nice form of this, would be Q, right? 4 times 3 is 12 pi epsilon naught, and it's divided by R in the AR direction. So after I get that, this marker's dying on me too. House cleaning on here. We're going to use this one. Now I get the E field, right? The voltage. From Q to D to E, from E, now I get V. It's going to be strict positive, so VAB is going to be equal to the integral from really A to B, magnitude-wise, of this, which is going to be Q over 12 pi epsilon naught R AR dot DRAR. Now, I'm just putting it down formally, but I took the E field and I integrated from the inner and outer radius to outer radius. You all with me? In doing so, what do I get? Well, I'm going to have a Q. I'm going to have 12 pi epsilon naught. And then I have AR dot AR is 1. And I integrate 1 over R, I get natural log, evaluated between B and A, natural log of B over A. And you can see, therefore, the capacitance is Q over V, right? VAB in this case. You all agree with that? I mean, any questions? I don't mean to go fast. I'm just trying to get to the points. And this was not meant to be in any way confusing. It's straightforward. So this is going to be, the Q's cancel, it's 1 over this, so I get 12 pi epsilon naught over the natural log of B over A. And that's it. And that's farads, by the way. And that's it. I didn't sting you if you didn't put units down. Do you agree with this, class?
You already put the
Yeah, there was already an F there.
You already put the
There was already an F next to it. What?
Yeah, I guess I did, but I'm going to level with you. I have seen the weirdest units. I'll see newtons sometimes.
Really?
I don't know how.
That's kind of weird.
You know, the truth is they're just guessing. I don't know.
You just guess a letter.
Try. All right, now the next part is resistance, right?
Yeah.
Anybody got any questions about this before we do resistance? And you can't just do R times C, remember? Because the only time you can do that is really going to be, or the only time you can do R times C, which is the epsilon over sigma, is if the dielectric and the conductivity were constant between the plates. Here they're not. You all remember me telling you that?
Yeah.
So you can't use that trick. So next, you do resistance.
I have a question on that actually. So if epsilon and the conductivity were like not functions of R, then you could do that.
If they were constant, not just my function of R, they can't be a function of theta or phi.
Oh, okay.
They can't be a function of anything. They have to be a constant value, like
So
12,
it'd have
5.
to be these like.
Then you would get C times R would be epsilon not, well, it'd be epsilon, whatever the epsilon value is, over sigma. What?
How would it change if it changes a function of phi and
What?
if it changes a function of phi and theta, we couldn't
What
do
changes?
Q. Wait.
No,
The
not
epsilon
No,
or
sorry,
sigma.
epsilon.
If epsilon is a function of the actual radial distance, right? It's still a constant anywhere within there, right?
Yeah.
Then it'd still be fine.
Okay.
As long as it doesn't vary spatially. Okay, then you can do it. Anyway, that'll work though.
No R, then yeah.
I don't really use that much, but it's nice, it's handy sometimes to do some checking. Anyway, next, here's the problem. So I have same geometry, which is nice because you've been thinking about it all through the exam. Inner radius A, outer radius B, right? And here I got a value of sigma that is sigma naught. What is it exactly? Forget me.
It's 10 over r squared.
10 over r squared, and this would be either Siemens per meter, 1 over ohm meters. That's the units there, right? So we want resistance. That means we want the resistance between A and B. We're curious about that. And the way we always do these problems, instead of starting with Q, we start with assuming I. It's assuming I is introduced with my little hole through here, if you want to think of that. I have a current I, and it goes in here and ground this, so it comes back this way. I flows out. It's a metallized surface. Y'all follow me? Once I have I need to get J. Well, J is equal to I over the surface area that the current's penetrated. It's spherically symmetric, so at a given distance r away, it's the same magnitude in the radial direction everywhere. Do you all agree with this, class? Follow me on this? You messed up J, didn't you? All right. So that's, I could be wrong about what you made a mistake on, but the only thing is you take that and divide it by 4 pi r squared in the AR direction. Now the units are amps per meter squared, and it should make sense because I is in amps, 4 pi r squared is meter squared. After that, after you get J, the next thing you're going to get is E. And E is simply J over sigma. So that's I over 4 pi r squared, and then it's divided by sigma. Sigma is 10 over r squared in the AR direction. Now this is going to be volts per meter. Y'all agree with that? Let me make sure you see this. By the way, I chose this particular problem on these values to make everything super simple. You with me? So now, one of the things you see is the r squared goes away. You agree with that?
Yep.
So that means your electric field is not a function of distance. The electric field for this one is just going to be equal to I over 40 pi volts per meter in the AR direction. That's it. Now I've got to get the voltage. And just like there, I integrate the E field from the inner to the outer radius. Do you all agree with that, class? So when I do that, because the E field's constant, to get the voltage V, I'll call it VAB, it's just going to be the magnitude of the integral of E dot dl from A to B. E is a constant. This is just what? VAB is just going to be equal to that E field times the distance difference. So it's that E field, right, times B minus A, or it's equal to I over 40 pi, and it's going to be B minus A, and that is the voltage, VAB. Finally, to get the resistance, AB, it's VAB over I. There's I, get rid of the I. You get B minus A over 40 pi, and that would be ohms. And that's it. Y'all agree with this? So that was it in a nutshell. In my opinion, the test was fairly straightforward and simple. A lot of the mistakes, in my opinion, are that you're probably cramming, that you get a little confused on how to do problems, either capacitors, inductance, or capacitance or resistance, because you haven't spent enough time during the class hours that are like between each class period. That seems to be the one thing I've taken away from talking to students, and just my own experience. When I sat where you are, I spent a whole lot of time doing every single homework problem that had a solution in the back of the book if I could. And I spent hours and hours and hours, but I never regretted that because that stuff stays with you. I mean, in the days when I took physics, all that stuff, I do them all, and to this day, most of that stuff is retaining, thankfully. And I don't use a lot of it all the time. I don't use kinematic equations or moment of inertia or rotation, but it stays with me because I think I spent the time when I was sitting where you were. Cramming is the worst thing. There are people, though, and I've met them, that they can just cram before the test, and that seems to stay with them. I mean, I'm not one. It's a rare person that can do that. All right, that. was it in a nutshell, the test. Now, let me tell you, we were doing, to finish this up, we talked, and I didn't put this on the test, we talked about the actual boundary conditions, which frankly, the tangent electric field across E-tan 1 is E-tan 2 always. In D normal 1, the normal component of the D field is D normal 2 unless there's a charge, there's surface charge density. And then you have to use that form A21 dotted into D2 minus D1 is rho S, but I try not to trick you on that stuff. I just want to make sure you know. We covered that. You weren't tested on it per se, and I've given you some problems. I want to mention this del squared business. Now, remember that there's always an integral and there's a differential form for just about everything we talk about, right? For instance, Gauss's law. The integral form is the integral of d dot ds over a closed surface is equal to what? It's really the charge enclosed by that surface. That's the general form of Gauss's law as integral. Do you all agree with that? All right. What is the differential form of Gauss's law? Anyone? That's integration, right?
Isn't it just,
Differential. It's divergence of d is equal to rho v. Do y'all remember that? That's how do I know that? Well, there's a form of Stokes, this is one form of Stokes, and the integral of d dot ds over enclosed surface is also the integral of divergence of the vector d over the volume. This is a volumetric integral. It's the same thing as this. Do you remember this from your math courses or not? Did you have this? This is a vector calculus kind of thing. So, if the integral of divergence of d is the same thing as d dot ds, then divergence of d must be the charge density. There it is. Div d is rho v. This is rho v. Y'all with me? Do you remember this? How many remember this is a differential form or the point form of Gauss's law? Come on. I put that up there. Kind of.
I have it written down. Yeah.
Yes.
I have it written down somewhere. I just,
I remember that. I'm trying to show you. Here's integration, here's differential, here's a point form. There's always two. Now, if you think about this, remember what is D? It's epsilon E, or you could say E is simply equal to D over epsilon. That's always true at a point. You with me?
Mm-hmm.
So, if you think about this, you remember the integral form of the voltage, if the voltage at infinity was 0, is V would be equal to the integral of rho V as a function of position, say R theta phi, and it's over 4 pi, and here it's just R, and that's the distance to this point of observation. I'm not going to make too much noise about this, and this is going to be times the differential, say it's spherical, so it's going to be times r squared, and it's going to be d or times sine theta, sine theta d theta d phi dr, and it'd be a triple integral of this. That would be the voltage if the voltage at infinity is 0. This would be over all the volume where the charge density exists. But I'm not trying to spend too much time on this. Do you all remember this? This is differential volume, right? This is the actual this times the differential volume would be the differential electric field from a little charge. If you integrate this, or not the electric field, the differential voltage. Now this is the integral form. I don't want you to focus too much on this right now. You can, but I want to tell you why I'm saying this. The differential form of this is the integral form, is del squared of V is equal to minus rho V over epsilon. Now that is, yes sir.
Would del squared just be the second derivative?
Del squared is in the back, it's called a Laplacian.
Oh,
Right.
I remember those, okay.
All right, those are
Yes.
double derivatives, but it's Laplacian, and they're different for cylindrical, spherical, and Cartesian. Technically, I think there are 10 separable coordinate systems. There's proloid, spheroid, spheroidal. Think of the concentric shapes that you run into. You know what an egg looks like, right? Proloid, spheroids. There's I forgot the name of it. Something ellipsoids, which are basically surfaces that have an elliptical type of shape to them. All these things have separable coordinate systems. all the things you can solve that del squared equation for. For instance, if you had a surface that looked like an egg, just assume that. It's not a sphere. But if you solve that and you get, make it the surface concentric with the major and minor axes of this egg-like shape, then you can solve, if there's a charge on that surface, you can solve for the voltage anywhere or the electric field anywhere. And so that's why they have these separable, you know what I'm talking about when I say separable?
Yeah.
Like all the vectors, the dot products of the unit vectors have to be equal to, anytime you dot any of these two vectors, a dot n dot a dot m, with n and m are different, you get 0. For instance, ar dot a phi is 0 always. ax dot ay is 0. They have to be orthogonal systems, and there are 10. And I don't think there are any more. This is one of those math proofs that they do. But they are separable, and I got a book upstairs by Spencer and Moon that details all this and why they're so important. Anyway, that's del squared V. We talked about the spherical problem. Do you all remember that? But in general, the only thing you're doing when you're solving this, and I'll just say this and I'll give you a few problems, is you're writing the differential equations here and setting them equal to the charge densities that they give you. A lot of times this is 0. And then you just solve the differential equations. That's it. Now, you're going to get into more of this later. I gave you some problems, and I'll give you some more about that. I've got about like a little 10 minutes. Now, really, the next thing we're going to talk about, we're done with chapter 3. I did talk about energy density and power density. Do you remember that or not?
Very briefly, yes.
All right, we'll be doing more with that, but energy density becomes very important, and I'll contrast that with power density as well. Energy density for electrostatics is just 1/2 epsilon E squared, that would be in joules per meter cubed. Power density is sigma times the magnitude of E squared, and that would be in watts per meter cubed. Dissipated power density.
Wait, it's sigma times what?
E squared. It's really J dot E. J is amps per meter. E is volts per meter.
I got that.
Volt in. That's power density. Anyway, so it'd be watts per meter cubed. Now we're going to move into the next chapter, which is magnetostatics, because we got to get through magnetostatics and part of chapter. This is chapter 4, and part of chapter 5 before this class ends. And now magnetostatics is a little more complicated for one reason. Yes.
So there are more than 5 chapters in this book, right? Does that mean we'll go over the rest in EMAG 2?
Yep.
Okay.
That's right. We'll pick it up where I leave off. And now this is magnetostatics. Now you've had a lot of this before. Static means nothing's changing with time. Magneto, it has to do with magnetism. That's all it is. So we start with, you remember when we talked about electrostatics? What's the first thing we talked about with electrostatics? Anybody remember? We talked about a very simple thing. We talked about the force between two charges, right? And we had Coulomb's law, Q1, Q2 over 4 pi epsilon naught. R squared was the force acting on either of those charges in opposite directions if they're the same, or pulling them together if they're opposite charges. With magnetostatics, we get something similar. So if you have a differential amount of current I, I'm going to do it, I'm not going to do the force form. I'm going to do it in terms of, you have your book here, right? Can I see your book for 1 second? I want to make sure, I'll give you a page number. I'll give it right back here. All right, so in the first part of this thing, in chapter 4, it goes through what curl is and really cross products. Y'all had cross products, haven't you? A cross?
Yeah.
I'll talk a little bit about that, but I think you've had it when you see it used. You had cross products, and this is the Biot-Savart law, and it's on page, it's right there. It's section 4.2.
It's 214.
Yeah.
So if you have a current I and it has a vector length here, dl, and you want, now pay attention to this because this gets a little hairy, and you want the actual value of, and he's going to do this, does he have H field or B field first?
He does H first.
All right, good. And you want the value of the H field at some point. So you want to know what the differential H field is here. Now just
What is
here-
H field?
H field is the magnetic field. All right, H, I'll explain this just like I did. The units are going to be amps per meter. That's the units. The H field is really like the E field. Remember the E field is volts per meter? The H field is amps per meter. Can you all follow me on that? I mean, that's the nature of it, but the formula is different. I want you to listen to me, and I'll explain this one. I have to define it mathematically first, then I can explain to you some of the how you can think about it. Okay. So mathematically, the differential H field will be equal to IDL. That means it's proportional to the magnitude of the current and the length of the current. I is a magnitude, DL is the length, differential. These are differential where technically DL is like approaching zero technically, but it has a vector direction. Then you divide this by 4 pi and this distance R. So R is going to be a distance from here to here. Okay? And it's a scalar right there. But then there's something very important. You're going to see IDL cross, and there's a cross product, and it's going to be AR. I think that's how he does it in his book. Let me take a look. I want to make sure. He's going to have A cross A1, 2, and I'll just show you what he's talking about. I call it AR. AR is always a unit vector, or A1, 2 in his book, is a unit vector that starts, it's actually from the actual current causing, this differential current causing the H field, and it's pointed at the point of observation, but it has a unit magnitude. You all follow me, class? Now, anytime you talk about a unit vector, I like telling you just AR. That's really R vector divided by the magnitude of R, right? I'm using a small r there. I can make it a larger if you want to, and it would make a little more sense. So that's R magnitude right here. This would be R magnitude. So if you just work with me on this one, make sure you see this. I don't want to go too fast. Y'all with me? So, yes, sir.
It says should it be squared?
It's not R squared.
The R.
I'm sorry.
Yeah, okay.
This is, I'm very sorry about that. I'm already getting ahead of myself. I think it is squared. And by the way, you remember for a charge, if you have a chunk of charge dq or q, and you're a distance r away, the E field is what? It's proportional to charge q over 4 pi epsilon r squared.
Mm-hmm.
These are called r squared relationships. Gravity is r squared. If you think about, well, I'm sorry. The force of attraction is r squared, all right, from gravity. There's a lot of 1 over r squared types of behavior. Now, I got to say one thing. You remember for gravity, it's k over r squared, m1, m2 is the force of attraction between two masses at either of the masses, and it pulls together. You're going to see that there are other forces in the universe. You know what the near force is? I want to just mention this because this is actually important. You guys have some appreciation. Have you ever heard the term near force?
Nope.
So if you think about the nucleus of an atom, somewhere down the line you had to have this. You realize the nucleus has what? It has protons and neutrons, right?
Mm-hmm.
Now protons are the same charge, right? They're both positive. So why don't they just fly apart? That's the near force. They're nuclear hooks that hold the protons in place. All right, now that nuclear force causes same charges to be attracted, but it is not proportional 1 over r squared. It's 1 over r to the 6th or 7th. It's an extremely short range force, but when it's there, it's holding those suckers together as tight as you can. The magnetic or the repulsion that you would get, the positives, doesn't happen until what happens? Until all of a sudden you hit the threshold of separation. And it's a temperature because there's vibrational stage where the threshold of separation becomes greater than the actual grab distance, and they blow apart because then the 1 over r squared force takes over. And then you get a nuclear bomb, basically. That's what, when you talk about splitting the atom, that's what they're really talking about. Those nuclear hooks are 1 over r to the 6th or 7th. I forgot exactly what they are exactly, but it's a much, much closer range force. It only works at very short distances. Then, just to complete the thought, what about, have you ever heard of the weak force that governs like nuclear decay? At a great distance, think about the distance planets are separate, no, galaxies are separate. There's a force that, I don't even remember what the value is. It's about 1 over like r to the 1/3 or 1/2 with a constant in front of it that dictates that type of force. And that's something that's beyond me to discuss because I really don't feel qualified. But that force works at great distances. You all with me? So the two forces we're talking about right now are electrostatic. They are 1 over r² type forces, or I should say fields, which will be proportional to forces. You'll see this in a second. So anyway, 8r is r vector over r magnitude. So just watch this. So it's really equal to I dl. dl is a vector. It's got a differential length and a sense to it. Crossed into, and I can replace r by, just do it yourself, r vector, and then I can say it's over 4 pi magnitude of r cubed. You all with me? And that, all of a sudden, now I don't have to worry about it. Unit vector, everything's taken care of, but r becomes a vector now. From the charge pointing at the point of observation. You good with this, class? With me? Okay, now, so that's the differential H field. Am I out of time? I think I got a minute. Yeah.
You're good. You got a couple minutes.
Okay, now, remember when we did this when we talked about electrostatics, we talked about the differential force between charges, then we found the force between volume of charge, and then we got the differential electric field, right? From a charge, a differential charge, then we got the total electric field by doing what? By integrating the differential electric field over the actual charge that caused it. Here, we're going to integrate over the current that caused this. You with me, guys? So I know I'm reaching here because you just got to test back, and you're probably not just jumping up and down. Give us more. Now we meet Monday, you know that. We don't have it off. July 4th is Tuesday. We don't have Monday off. I'm just telling you this. Somebody asked me,
What's the chances you'll do online?
The chances of Zoom.
God, I wish you would have asked me that at 8 o'clock. Because my other class is already, you're in the other class. We didn't talk about it.
Yeah.
You took a test. I mean, what can I do?
Yeah, well, yeah, it's a test.
I would love to do that. But I tell you right now, I don't think my department chair is there. And I didn't poll the other class. Let me
Again, I'm
just,
certain they'd agree.
Yeah.
yeah, that's the problem. Your word doesn't work with him.
Yeah. I don't know. Other professor said he was going to do Zoom as well.
Yeah.
so-
Who?
Geiger.
Geiger and then my
Schneider?
professor, Geiger and my professor for Digitron are.
Who is he?
She's a GTA.
You guys, you're straight with me? They both did?
Yeah.
Yes, sir.
Geiger.
Yeah.
Geiger canceled
He's doing,
completely. I think, or for me.
All right, guys,
He canceled
listen.
your class?
Now,
Yeah,
don't
he-
get me in trouble for this. I'm going to ask politely, and I got the camera fixed, if I didn't have that camera fixed. But does anybody object to having a Zoom class? You don't mind?
That's fine.
Now, wait. I got to check on this. I wish to God you would ask this at 8 o'clock at night so I could ask my other class. All
Are you
right.
in their group me?
Huh?
Are you in their group me?
Am I in their group me?
I'll
Yeah.
ask him.
He is.
Yeah, ask them.
He's running. Aren't you the guy that does it? Or no, you, the other fella does it.
That's the guy.
Michael Smith.
Great.
does it.
He's got like insane camera and stuff.
All right. Well, I'll tell you what. Wait. Yeah, go ahead and ask him, but don't promise him because if I don't get clear with him, I can't. But if already other professors have done it, see, there's my ace in the hole. I just say, but they're doing it, and he's like, they are. How dare they do? It's easy to get permission. All right. Easy to get forgiveness, hard to get permission. However, if they know you're trying to get away with something, they'll hammer you. I mean, you can lose tenure, you can find yourself walking out without a patient. Anyway, I don't do that kind of stuff. But I will check.
Okay. Thank you.
All right,
But at the
now-
very least, you'll post some sort of recording.
What? Oh, yeah. I mean, but I'm going to, guys, please show up, all right? Because what's can happen to me, I doubt it will, but so I do a Zoom lecture, there's nobody there. And why are you doing a lecture? Well, it's recorded, they can watch it anytime. See, that's when it gets really hard to sell. I don't think it's gonna happen. All right, just turn on the camera, say hi. I'll try to do it on Monday. I'm out of time. But I'm gonna give you some reading. I wanted to do one problem here, but I don't have time. Now, are you guys getting something out of this class? The way I'm teaching? Any complaints? I'm trying to be fair.